Okay, so this evening's presentation is on propless tunnel openings design for HS2, which designing these openings in tunnels is something you've got to get right. And we'll hear in February's evening presentation about where you can have some problems. So looking forward to speakers tonight. So our speakers are Michael Grenier, Head of Tunnels for Skanska Costain Strabag JV. Michael serves as the Head of Tunnels at the SCS JV, where he has led the delivery of all tunnelling works for the HS2, lots S1 and S2, since 2018. For the past 22 years, he has worked in tunnelling for Zublin and Strabag and has contributed to major international tunnelling projects such as Copenhagen Metro City Ringling, Hamburg Metro, and multiple sewage infrastructure schemes in Israel. Apologies if I get this pronounced wrong, but Dominic Hari, TBM Tunnelling Design Lead for Strabag. Dominic is a civil engineer of Strabag AG who has specialised in tunnelling, geotechnical and structural engineering. He has done design and consulting for international infrastructure projects. Since 2017, he has been the TBM Tunnelling Design Lead for HS2's London lots S1 and S2, and has been responsible for the segment design, SCL structures between the TBM tunnels, and interfaces to portals and shafts. And the third speaker tonight will be Xavier Torello Siriano, Senior TBM Design for TYPSA. Xavier is a civil engineer specialising in structural, geotechnical and tunnelling engineering. He has broad experience in structural design, TBM monitoring, urban instrumentation and planning of major infrastructure projects. Since 2017, he has been Senior TBM Tunnel Designer for HS2's London lots S1 and S2, contributing extensively to tunnel lining segment design and testing. So, first speaker, please.
Thank you very much for the introduction, and good evening to everybody. Thanks for the large attendance. I didn't thought that so many people would come. It's also good to see that a lot of faces are known. I guess that quite some in the audience had one or the other contact to the topic we're speaking about tonight, either in the design phase or the execution phase. Design and construction of large propless openings in segmentally lined tunnels using special segment is the title of the presentation tonight. It's a little bit of a tongue breaker. I will not repeat it going forward. When in terms of terminology, we'll use like special segments, opening sets, or shortcut specials for the solution that we chose and that we will present you now in the lecture tonight. In terms of the agenda, we do first a project introduction and an overview that is maybe a little bit more extended and goes a little bit away from the main topic here tonight, but it gives you a little bit of impression of what we did and leads into the requirement that we put into the design. Then we do the jump back in time, go a little bit the journey of the opening sets that were designed. And the agenda tells a little bit the history. So first was the design, then there was quite intensive structural testing, then followed by the fabrication of the segments due to being quite a complex solution. Also quite an element of quality control is involved. And then we come to the construction element, and at the very end, we want to summarize a little bit our experience. We try to we put a little bit more focus on the practical elements, not only the design elements. Want to get really over a little bit of how the construction also was. And during the summary and conclusion, draw a little bit what went well, what maybe can be improved, or mainly it's actually watch outs, and then followed by a closing statement. Project introduction and overview. So the HS2 London tunnels are carried out from a mainwork civils contractor sites by the joint venture Skanska Costain and Strabag. On the design side, we have got a design joint venture that we call Design House, which consists of Arup, Strabag, and TIPSA. And we actually take a good pride also of the NCE tunneling awards that they've been winning. In 2023, we won the Innovation in Tunneling Design and Construction, actually for that very opening sets that we're speaking about tonight. And in 2024, we won the award for the Tunneling Team of the Year. Only with good people on all sides from design and construction, you're able to design, implement, and do such a solution. Here's a little bit the overview on the project overall. So as SCS London Tunnels, we're building twin bore tunnels from West Ruislip to Euston in the east, in the center of London. The majority of our tunnels are bored tunnels. We've got altogether 42.2 kilometers of tunnels, which is in a magnitude actually what all across the rail was together. Due to having a little bit larger diameter, we produced or are producing double the amount of excavated materials. It's quite a lot of works going on. We also have got some shot grid lining works, which I will not touch tonight. It's maybe going a little bit too far away from the main topic, but for sure there will be also a presentation at one point around them because they're also quite interesting. On the left-hand side, you see the Norfolk tunnels, which consist of Norfolk Tunnels West, shown in blue, and the Norfolk Tunnels East in purple. In the Norfolk tunnels, we've been operating 2 TBMs starting at West Ruislip, making their way to Green Parkway. And on the eastern side, we started at Victoria Crossover Box, which is close to North Acton Station, with 2 TBMs. All of that bored tunnel activities are finalized. In the very middle, you see at Green Parkway, where we retrieved all 4 shields with a big lift arrangement that you might have seen somewhere in the media. And there's a little bit some pictures around the finalized activities. Going to the right side, we've got the Euston tunnels. We're very well prepared for that ones. And want to launch the TBM back end of this month, beginning of next month, the first one, and the second one will then follow in March. The activities for the Euston tunnels will be served from our Atlas Road logistic compound, where we earlier built a logistics tunnel in order to serve then the activities and the machines working out from S4 Older Common Station. Segmental lining is coming in for Wilson Euro Terminal and is then brought to the construction site. This evening's lecture is mainly focusing on Norfolk Tunnels West, as we are much more progressed with the works and can show a little bit how that one went. Beside the bored tunnels, we have got along the Route 7 shafts that are sitting all along the alignment, and also 52 cross passages, of which we finalized 34. But beside that bored tunnel activity, SCL and cross passages have been constructed concurrent to the TBM works. We have got also 5 other main activities. One of them are the invert concrete. In total, in the Norfolk tunnels, we've been placing 54,000 cubic meters of concrete. Also, that works have been carried out in concurrency to the TBM advance. Hence, we had to use a solution that allows as well other construction activities and mainly to serve the TBMs. This is why we chose a bridge solution, where you see some pictures impression over there. Why did we go for that solution? 2 main drivers. Foremost being time, doing it concurrency saves you the time to have that one done afterwards, but as well logistical reasons, because with all the activities that we've got ongoing in the tunnel, there's quite a lot of action, and the flat surface gives you much better possibility in terms of logistics, also, but also for safety reasons. Then what we have got currently ongoing is the walkway construction. Walkways are built all along the tunnel. They're divided in 2. One is the maintenance walkway, the smaller one, and we've got an emergency walkway. Also, this one is quite a considerable amount of concrete. Works are currently ongoing. For this, also, we chose a solution that still enables logistics and traffic through the tunnel. So it's a bridge form system on which we cast and left and right side the walkway. The works are executed by subcontractor MPD together with us. So far, we have been doing out of that one 25% roughly. We've got now 2 bridges in operation, and in February we'll bring a 3rd bridge in operation, building that one in the Northwest tunnels. Then also related to the openings, all along the segmentally lined tunnels, we have got sliding door frames arrangements that facilitate the fixing of the doors later on. We've got 75 of them within the board tunnels against the segmental lining, and some more against the shaft or at the shaft areas. Steel fiber reinforced concrete will be used for that one. We're using a modular formwork system, steel formwork system for those, and that works will also start in February this year. Coming a little bit closer to the connection topics, I mentioned the cross passages before. All together with a big element where connections are taking place between segmental lining and the other structures. We've got all together in the SCS volume 129 openings that in a permanent arrangement have got a cross section of 6, which are the cross passage, up to 28 square meters in 9 different sizes in varying geology. I think everybody who's involved with or has been involved in one or the other way with making connections between segmental lining and other structures knows that it looks nice and neat and quite simple on an outline drawing. It looks very elegant then in the final design drawing, but the way to getting there is quite complex sometimes and can create a bit of a headache. So there's quite a lot of thinking behind, giving you a little bit of introduction maybe at the shafts itself. We've got 2 different shaft arrangement. If you look at the left one over here, there's a main shaft that sits on the downline tunnel, and there's a satellite ventilation shaft that sits, sorry, the other way around. The main shaft sits on the upline tunnel. The ventilation shaft sits on the downline tunnel. So, and with the other arrangement that we have got where the main shaft structure sits in the middle between the 2 bores, and we have got a 4-finger structure that connects on the top. In the left arrangement, the shaft was built before the TBM arrives. So the TBM drives through the shaft, which is filled with formed concrete. In the right arrangement with the 4 fingers, it's either that TBM is first and then the fingers are constructed, or the other way around. Both are possible. Why did we have 2 different solutions? Mainly 2 drivers to that one. One is the surface space being available. The other one, the more harder driver, is the water-bearing conditions that we've got partially, which would make the right arrangement a little bit more difficult in execution. The fingers are executed with SCL. So in 2 shafts, we have got the left arrangement, which are the water-bearing ones. So giving you a little bit an outline on the different connections. First of all, we've got the cross passages. They are serving for evacuation in case of fire or any other incident, and at the same time are there for systems equipment storage. Then we've got the ventilation openings that are fans are connected to those which are then for smoke control in the event of a fire or for temperature control in a stealth train situation. It's quite astonishing how much air can go through there. So 200 cubic meter per second is the max performance. That is, I was Googling before, like 9,000 top fans that you've got in the private use. So it's quite, if you stand there on, I think you've got quite a different hairstyle afterwards. So these are quite big openings. The 25 square meter one is where we have got a closer look afterwards. The smaller ones are soon to be opened, but not yet done. And then last but not least, there's also a shaft passage. That one serves as an access point for emergency services and is roughly placed in 3-kilometer intervals along the route. So that is roughly the scope that we are doing. Now I take you a little bit of jump back in time, coming over to the design. As you see, with all the different activities, when we started the design, and now we speak 2018, where we've been in the ECI phase of the project, We came up with quite a healthy suite of requirements from the construction side that we discussed with the designers. We told them at that point already, we wanted to build cross passages and the inward concurrent. On the opposite, we want to construct shafts and tunnels independently, because in such a large-scale project, timelines are changing, and independency of the different activities as large as possible is very beneficial. Then we also want to have the flexibility to change construction sequences, let it be coming from the tunnel or let it be coming from the shaft. Apologies. Cost efficiency was also main driver with the 129 connections. That is quite a lot. So you need to have a solution that is also cost effective. Then facilitation of groundwater mitigation scheme close to the connections. That is, in our case, mainly then the cross passages. And as we have so many openings, the focus was always on a standardized solution, trying to minimize temporary works as much as possible. And the solution should be in a way that it minimizes the risks during the installation and the opening. So with that healthy suite of requirements, I'm handing over to Xavi, who will give you a little bit further insight into the design.
Good evening. Thank you for coming. Basically, we are going to make only some points related with the design and precisely how we come to this solution. No? Precisely to illustrate the variable solutions and how to accommodate for a standardized one. No? Here only I'm showing one of the profiles in Northern Tunnel West, the first part of the project that currently is more progressive in terms of construction. No? Here we could see the variability in terms of tunnel cover between 10 to 30 meters. We have to deal for different geotechnical conditions. We have over-consolidated clay, sand layers, chalk, and all the topic related with the temporary works later for made the cross passage, and also reaching points with near 4.5 bar of water pressure. No? The other sections, Northern Tunnel East and Eastern Tunnel, is basically in a London clay environment. But we are going more to focus on this section that's really in terms of governing the design is more illustrative. Okay, and then how we come to this solution, no? Basically, as Michael has explained it, no, for concurrency of all the works to be developed inside the tunnel, we were exploring how to achieve solutions to have an unobstructed cross-section inside the tunnel, basically to make the different works that Michael has explained it, that go inside the tunnels, no, to be executed together. Then we are thinking on looking for no propping. Another point for this design is looking for one support system. What I'm saying with one support system, basically, the conventional approach is using some kind of solutions of temporary, no, for deal the section forces of the tunnel lining around the opening, no, and later coming with collars and different kind of final solutions, no, to fit around the opening, no. Here now is where could we combine it, and as I have explained, you know, we have to deal with the variable loads and the variable conditions, no, as we have explained it, attending the longitudinal profile, the geotechnical conditions, but also we have to deal is we are going to explore a solution that going to be temporary and permanent. We have to deal with the temporary loads during the cross-passage execution and also the long-term conditions, no, that we are going to have once all is finished, no. Conclusion. When we look at the state of the art, no, basically what is conventional, thinking on some kind of temporary different rings, having some internal frames that later are going to be removed, permanent stills around the openings, or also combination of props and that. Also, something that is quite standardized using fittings, but here we have an important topic. We are in conditions, we are in soil conditions, we have relatively large low conditions, no, and then these solutions are we need to go more away, no. And then that's where we develop it together with construction team, no, how to look for a new and reliable and flexible system, no, to achieve all these objectives, no, that we are looking for. In terms of requirements, I'm going fast. Basically, in terms of durability, we have to achieve the 120 years. Fire resistance, no? We're here attending the interoperability for railways. We need to achieve the Eureka curve. This is important, no? Because as I have explained it, the solution has to deal in the final stage, and that's fire. Later, we're going to explain is a critical point and has been testing, no? And water tightness, no, with a strong limitation of leakage, no, and no acceptance of relevant leakage around the whole road. Okay, I will going to go fast with that, not going to be too deep on that, but basically the topic, once we have a beautiful circular tunnel, later when we make an opening, structurally we have to deal how the actions and the section forces are redistributed, no? Basically, the main topic is that around an opening, you have to bridge the whole forces that come from the rings and have to transfer to the sides, no? This generates an increase and localized large section forces, no? And also generate some tension forces next to the opening, no? But basically, here we have to, what we could make. And then the first idea is all these tunnel segments works more together. We are just looking at this simplistic sketch, no? Ideally, if we could deal that is more near to a pipe, we will have an easier redistribution of the section forces around the opening and a better structural performance. And the solution has what we needs to look, no? Using some combination of some kind of shear connections between adjacent rings, and then attending we have large load, these large shear dowels not to damage the segments, no? And then using some kind of pre-stress that only could be temporary, no? Around the opening for deal in the temporary stage, no? And then the design basically was a process, no? That we ran geotechnical models, basically the two extreme cases, no? Because software always has some limitations, basically for a full connected joint or a continuous pipe, and an extreme, on the other extreme case between open joint, no? Basically, all this process with praxis modeling is basically to take into account the geotechnical conditions, the stage of construction, short term, long term, no? And basically, all these processes with the geotechnical models is to obtain a lot of derivation that all later is going to be used to fit up the structural model, no? And the structural model, what is the difference, no? Basically, in this structural model, we could use the particular elements that is connecting between the rings, no? And here is basically that we take into account the nonlinear behavior of the connection elements that later we are going to explain. We take into account the sequential construction excavation, no? And then it has been a process, iterative, no? That between the extreme cases obtaining from the geotechnical model that has a simplistic approach, no? With a continuous pipe, complete disconnected segments, no? To achieve a point, no? Sorry, that we arrive at the structural element model, no? That take into account the overall behavior and takes the reality of the connection elements in there. And what are these connection elements? When we come here to the solution, basically, a large shear dowels that are connecting with the tunnel segments. Second, use of pre-stressing rods that are going to be considered temporary during the construction works. And third, and the more important, these huge shear dowels in a concrete segment, how we have to transfer these large loads. And then inside the tunnel segments, there are embedded steel profiles that has different missions. First, and the more important, to transfer the local large loads of the shear dowels. And second, are used to also have the tight tolerance we need to assemble the segments in the tunnel segments. And the third point, the rebar case, as we have explained, we are in a soil conditions, large section forces. We have to deal also with the temporary loads, not relying on some additional temporary structure inside the tunnel. Then we need a large rebar cage, no? And also here is seen, no, that the concrete will rise it up, the concrete grade to around 70 to deal with all localized increase of section forces around. And the main business, basically, all could seems too complicated, but basically we are transferring all this complexity of tolerance of these steel elements that later we have to fit like a clockwork in a tunnel, and we are moving works that could be complicated in a tunnel to a factory, no? And as Michael have explained it, how was this process? No, this process started here in February 18. Later, we started with the detailed design. Here, the main goal was the design approval was around April 20. With that was a process of contract award, casting of test assembly, and mold delivery. But for me, the more important, and now we are going to explain, is all this process of testing. You know, that we conducted some tests that now we will show some beautiful pictures. Testing for fire cure with fire, testing of the cage, because you have seen the pictures, and then how the concrete flows inside and to be reliable. Also testing for these large particular connections, and also to be tested as a long-term and fire resistant. And finally, we are also, you will see some destructive quality checks, no, to see that the concrete is there, no? And basically, we arrived to the 22. We have also an important topic, no? That when the first TBM was launched in North Montana West in October 22, and basically the first installations of special segments was end of 22 and was around 2023 that the opening works has started, and today we are explaining about that. And then Dominic will explain you about this testing.
Yeah, good evening. Structural testing. So now that we had the design, our client HS2 were wondering if we were sure about the performance, and said, guys, would you please check if you can do some real testing, because the stability and the fire resistance is some really important topics for us, and you have never done this before. So please think, what could you do? And so we went into us, we thought a bit, what would be possible, what could we test? And we thought about a setup, which would be a shear test that we said, okay, we have a strong direction, which is a tangential one, but we also have a weak direction, which is a radial one. And some of these connections, they are pretty much loaded in radial direction. And so how can we test what is the performance? So we set up a shear test. It's called Pesco shear test. We talked to Serip in France, which is a laboratory there. We planned to do 6 tests, 2 shear tests in cold conditions to have the load deflection behavior, 2 fire tests under constant load, and 2 shear tests finally with the fire tested segments. So they build us a rig. You see it there on the right. The rig produces a shear force in the middle of the connection, and it reduces the bending there. You see all these hinges. So it's freely rotating. You only have these 4 points. You note here from the top, and you can measure here next to the joint what are the deflections. The second test with which we came up is that we put these test pieces into a furnace. This is a bit more complicated, so there is a lot of planning related to that. We had to insulate all these supports that they would not collapse during the fire, but the interface here is really just a little steel rod, so it's not a massive support, it's freely rotating there. We also did measure here the deflections, so there are 4 sensors. You can precisely, within 1/10 of a millimeter, see what is the what is deformation. We had the client's fire, 170 minutes up to 1200 degree. And the outcome of the test was that we had these two segments here. One is pretty intact, the other one looks a bit ugly, but the main point for us were these results. So 600 kilonewton is approximately the maximum loading that we had in the design in the weak direction, and it performed pretty well during fire. So this is the deformation over time, up to 1.6 millimeter. Technically speaking, this is nothing. So it did not deflect. And the other one, the ugly one, even performed better. So this is approximately the maximum loading in any direction that we have anywhere in the segment tested in the weakest direction. It was up to 1 meganewton. We were also did some pre-assessment before the tests. So we set it up in finite elements with a finite element code Abacus, which have very advanced material laws. So we have some specialists in the offices that can operate this. We tried to derive a load deflection behavior, which is this one here, and we expected it to be somewhere between 2 and 3 meganewton per connection. It's looking pretty complicated, and it is pretty complicated, but you cannot do this with the more simplified finite element software. What was the outcome now? A little comparison between what you can buy here from the shelf. This is these towels, some of you will certainly know them, and this is our solution. If you test these towels, they work pretty well in tangential direction, but in radial direction, which happens sometimes, it's quite limited. And whatever you are doing here with the rebars, it's not going much about 200 kilonewton. And with these pieces here, steel cast in, you have a much stiffer behavior. So you see it's going up to 1 meganewton, 1.5 meganewton, and you have 1 millimeter deflection. So it's almost nothing. And the graph is even cut here on the right-hand side. We loaded until approximately 20 millimeter, but these pieces, they never failed. They just deflected more and more, and we stopped the test after a while because it became unstable, and we did not want to risk the rig to collapse and to damage the equipment there. So the behavior was really superior. We were happy about this, and we have a very stiff, high capacity connection that takes tension, fire, and it has almost no loss about in the afterwards tests. Even if the segments were damaged before from the fire, the capacity is almost the same. So the steel healed somehow, and the concrete was only a filler. Yeah, fabrication and quality control. Some impressions from the factory. How does it look like if you cast these segments? They put these molds here outside the carousel. So usually you have these segments revolving endlessly around, and the people do different production stages. But we put them here in a separate area. So you have something static because we didn't have to produce so many of them. It did not count. We had some the build of these cages. It wasn't that difficult. They looked difficult, but we included enough tolerances, and so in the end, no one complained from the factory. Once they complimented how to put all these rebars together and the steel, they made it quite easily. They were stacked here, and then they fit into the mold. You see the rebars are pretty dense, but the next question of our client HS2 was, please make sure that you cast these properly. You see it here. It's looking quite thin. Yeah, it's the reinforcement is almost disappeared, and so we took this thing here. So we cut in two directions. One's in this direction, one in the other direction. We checked, did the concrete flow everywhere? It's pretty clean here. And the enlargement here of the other picture, you see the quality is pretty perfect in my opinion. So the supplier did a very good job here, and all the doubts were cleared. It's possible to do something like that. Yeah. So in the end, we had dense rebars, but we didn't find any voids. We had a concrete mix, which was 10 millimeter grain size, and we checked the feasibility of everything there in a 3D model before, with all these rebars and steel elements properly designed. We checked for all of these gaps, and in the end, it worked out as we wanted to have it. So finally, now to our main slides, which is possibly the reason why you all came in tonight. What did we construct with these things? Yeah. First, we had to install them somehow in the tunnel. You see it here. You have to insert these dowels and you have to insert these tie rods. You can use it. You can do it either from here. Sometimes the guys put it directly into the segment. The TBM lifted it here with a vacuum plate. Then they were inserted. We have enough tolerance here, so it was possible, even if you see 9 here, it wasn't overly complicated to fit in. Then the next step was we wanted to apply the pre-stressing. We did it when directly after the ring build, so the ramps were still here. You pre-stress, then you have it directly in contact with this one here. And since we are not using any packings, you also activate the friction here. Some impression how such a dowel does look like in comparison to the standard click dowel. It has a corrosion protection, is much larger. And here you see a grouted pocket. So this is a finalized connection. Now to our first real large opening. We had to launch the NDE TBMs here from the Viras shaft. Then we, one back. Then we have to make this cross connection here. This was an SCL cavern before. Then it was filled with foam concrete and the TBM will pass through it. Unfortunately, the TBM will cut almost everything here from the cavern, so there is not much left afterwards. We were challenged by our client that we should accelerate the cross-connection construction. We previously had it in stages, but they wanted to have a single advance, and they were also not in time, so they had an incomplete secondary lining. So it was a question, do we try some temporary works, which was against our initial intention that we never use temporary works, but it comes with delay, health and safety issues, and possibly the stiffness is also an issue. So we said, okay, reconsider the design, add some further connections between the existing special segments, and try to work out, does it work like that? Another impression, how this does look like. You see here the main shaft, Viras, Victoria Road, and Sildery shaft, and this is the cross cavern where the second TBM launches here. Both are 9-meter TBMs. And this is what we finally did. The green segments are the special segments. These little things are the connections that you saw. And we inserted one row here in the center line and did all the calculations. You see a model here, how it deflects. And we concluded, yes, it will work. You can continue like that. Some impressions from the excavation. I think the guy here had quite fun to dig all this down. It was done pretty quickly, I think in 2 days or so. And I'm happy that he stopped just before the lining, that he did not dig any further. You also have to imagine the TBM is 165 meters long, but they started with the excavation when the cutter head was approximately here, so a few meters advanced, and all the rest from the TBM was still here. So in the picture that you see here, when it was fully exposed, you still had all the gantry wheels rolling over the segments, which were spanning approximately 11 meters here. I was there and it looked quite impressive to me. You see here it's supported, or this is the TBM grout between the lining and the primary lining of the cavern. And you also see it has an open end here, so this is the incomplete secondary lining. Yeah, so the support was, well, it was supported somehow, but not massively by this structure. So since we were unobstructed, the works went pretty straightforward. You can install the waterproofing, the rebars here, and finally, this is the opening. This is the connection to the shaft. The segments behave quite good. We did not measure any deflections. We did also not see any crackings, so the solution worked quite well. And the doors here, they are not yet installed. This is then the completion of the connection. Then our top connections and the two other shafts in the Northwood tunnels. A little reminder. We have this main shaft, as Michael said, with a TBM transit, and we have the other one with a ventilation. What you do not see here is that the Chiltern railways is almost directly above this shaft. So there is already a constraint, which is why the shaft has a trumpet shape. We are below the railway here. And main thing is our two teams, they want to work independently, not because they don't like each other, but because we want to avoid the interface here. You see here, this is the SCL shaft. Here's the D-wall shaft, the two possibilities that we had. The work stream that you can work from above, it's only possible because we said this is already our final support of the tunnel rings. Yeah, so you can install this collar here. The temporary opening size is equivalent to the permanent opening size, and only at the end we will remove the segments. One second. Where's the next one? Yeah, so this is the 28 square meter. We cast the secondary lining. Finally, the segment goes out here. And you see the collar ends here at the edges of the segment. We also have quite some transition here. So we have the flanges here and here. These are three different angles. So we go from a cross shape to a rectangular shape here in the top. And since our colleagues from Ray Systems, they were so persistent with the sufficiently large connections, we took on the motto, make our openings great again. And I thought I could compare this to Donald. You see him here, 75 inches tall, but if we shrink him properly, it's just here. Yeah. So in case you want to have some of our merchandising articles, make our openings great again, I think there is a discount for the attendance here tonight. We are happy if you take any orders. Back to serious business. The excavation and monitoring, also some impressions from the excavation. We tried to measure some deflections. So you see here a 3D laser scan, or the difference between two 3D laser scan, one taken 3 months before we started the works, and one when everything was exposed. The tolerances here in the deflections, it's approximately the tolerance of the scan. So we were below 10 millimeter, not much more happening here. Yeah. So also it worked quite well. And we continued with the works. You see here termination detail for the waterproofing, all done from above. They're installing here the sheet membrane. And finally, the finished cast with the different sides here. The guys are just doing the final works before the fun part begins, which is that the segments do come out, which is then again the part of our construction guy, Michael.
So Dominic showed you how it was looking above ground. Now we're jumping back to below ground and not on the surface. So when we did the openings or created the opening itself, we had two ways of doing that in South Ruislip due to the ongoing construction works at that time, and we could not block the tunnel. We chose a solution where we facilitate the tunnel traffic. So we built a crash deck, and we had the possibility to lift segments out through the shaft itself. So we core drilled the segment into smaller pieces, put some regular anchor in it, lifted it out. The whole activity took then 16 days for the install and the removal of the crash deck, and 8 days for the coring and lifting activity. At Mandeville, chose a slightly different methodology to that one. We decided to block the tunnel, made the area of the opening in exclusion zone, did a few core drills and a saw cut, and then started demolition with an excavator. That one took then 9 days all in total. So one or the other might wonder now, why did I come all the way here to see a little bit of cup drills and saw cutting and a hammer? That is exactly the point. We invested a lot of time at the very beginning, and we wanted to make it afterwards simple as possible, straightforward and in a safe manner. So in that case, the target was to not have it spectacular with big structures, but just a few cup drills, a few days, and the connection is in place. I think they're looking quite impressive. In the middle, you see the South Ruislip one, where we created a small underground dome with the view up. It's a very nice view. Whenever I pass by, I take a picture. I've got, I guess, 15 or 20 of them already. It's quite impressive structure, and also need to be mentioned with the 28 square meters. I think we created one of the largest openings done in a segmentally lined tunnel. So that is quite a massive enterprise, and must say that went all quite well over there and straightforward. Last but not least, we didn't put so much focus in it. There was already an earlier presentation back end of 2024 regarding cross passages, but for sure the cross passage has been a main element as well. Out of the 129 openings that I mentioned previously, 108 are cross passages. So the cross passage brought actually the mass production element into the connection. So as mentioned, 34 cross passages executed, gives you the 64 openings. 11 of them have been treated using artificial ground freezing. In the middle, you see in the model the arrangements of the freezing pipes. On the left side, you see the drill rig, and on the right side, how the freezing looks like. All of that one, again, has been done in concurrency. During the design of the segments, we kept windows in the rebar for durability topics when we would not wanted to core through the rebar over there. 6 cross passages have been dewatered or depressurized, 2 of them from surface, the 4 other ones from in-tunnel. Another benefit of the opening set solution is also that there's no supporting color in the opening needed. You see over here, there's just a segmental lining which is cast against, but there's no collar that is holding the opening from the top part. And also here, we had a minimum of deformations. Ballpark figure, we speak about 15 millimeter when opening it in London clay. When freezing, there was the freezing, the ice pressure on the rings, but there we're in a range of 25 mil max, which was well within the design assumptions. You found also here, Mr. Trump again, he looks much greater in the cross passage, but it's still small compared to the opening. Then the cycle for the cross passages, we did some core drills, secured the segmental parts, took them out with an excavator, Then shot grid lining with steel fiber reinforced concrete, sheet membrane for waterproofing, and then doing the final secondary lining using a curtain shutter system. In terms of durations for that one, in a non-treated area, so this is mainly the London clay ones, we speak roughly about 4 days preparation works, 20 days in execution, 9 days for the waterproofing, and 17 days for the secondary lining. With the freezing pipe arrangements, you've got additionally roughly around 38 days on top for the drilling of that pipes, and then the cooking time for the freezing, roughly 50 days, and a slightly longer excavation also due to the changing of the properties of the soil. Summary and conclusions. The advantages of the solution, it's a quite quick ring building time. So the installation that Dominic showed you before, putting the dowel in, pre-stressing it, took us roughly 45 minutes longer than a normal ring build, which is, from all the solutions that I had so far with embedded solutions, is by far the fastest one. So it worked out quite well also with the tolerances. At the end of the day, we've got a permanent and fire-resistant opening support. The high flexibility that we showed you also with different approaches and methodologies is complying with very load and construction sequences. Maximization of the space that facilitated all the other activities within the tunnel. The groundwater mitigation schemes, so there's quite a lot of drilling through the segmental lining. And the minimization of the cross passage opening size that I mentioned before with the omission of the collar. And as aforementioned, also the independency of the different working activities in the shafts. In terms of watchouts, for sure it's a very complex solution. It's not a standard one that requires an early coordination between designer, contractor, and manufacturer, by far more than other solutions for sure. Also, the rebar, you saw it, it was quite detailed discussion between ourselves, the designer, the segment producer, but also the producer of the molds and the jigs. The testing for acceptance is on the critical path. What Dominic showed you, if such a test fails and you not have got sufficient flow in your program, it is a little bit of a challenge. Then I went to the construction teams and I told them, okay, I'm doing a presentation at the BTS. I want to know now what didn't work. And I want to really know what didn't work. And I told them, oh, I will not tell you. But at the end of the day, I was really astonished when you speak with them what the comments was. One is the steering of the tailskin clearance, steering of the TBM tailskin clearance. If that is not fully aligned, it's getting tight and it's a very rigid solution. But you have got that at all cross-passage solution that are embedded, because you've got fixed ring positions over there. Depending for the cross-passage, you lock 3 ring positions. 6 rings position was then in re-res, which is quite a lot. Re-res was also a bit challenging because we just started the drive. There was a curve. So over there we had some interference between the tailskin and the segments, which leads then to some spalling, but repairable in that way. But it was not a generic topic that we had a large amount of cross passages or openings where we received that damages, but it is a watch out. Then the team said at the beginning it was a bit difficult with all the different rods and stuff. We had designed 36 millimeter rods, 39 millimeter rods. Had to be properly marked. One time it was also wrong installed. In that case, it didn't really matter because the loading was not so high. Learning was over there. Next time, let's just go for one size, makes it easier. Then the injection hoses sometimes in the pockets have been clogged or blocked. So either we drilled them. If that was not possible, we drilled a packer and could inject then. So also that one was resolvable. For sure, quality control in the precast factory. You saw it's a quite dense rebar arrangement. Also important is consideration or that there's enough tolerances in the connection. We got that pitched quite well. So we're scratching our heads a little bit up front, but that was working out well. again, the main point is that we transfer temporary site works to the precast factory that takes it away from the construction site then. And the last slide, a little bit of closing statement. I know it's slightly wordy, but in my opinion, the correct decision was made. Solution successfully was implemented. We facilitated logistics with independent work streams. We had minimal deformations, and we had compliance with all the tolerances. We facilitated off-site productions that we wanted to have. It reduces additional other permanent construction works around the opening itself as a support. But as mentioned before, it requires coordination between all parties, heavy geometrical checks, even the interface with the TBM, for example. We've got a lot of things to regard over there. And the early assessment of all constraints from production to installation is very important, because if you make a precast solution, if you do a mistake, you've got a systematic mistake, and that is challenging then. Recommendation, where is that solution on our opinion the right way forward? It's highly recommended for projects where you've got a lot of connection works and also high capacity connections requirement, because you saw the testing arrangements. That is a little bit of an invest, but with all the different connections that we had, you put it overlay it, and then you come to quite a commercially attractive solution. But for sure, if you've got 500 meters of tunneling in one opening, it's quite an invest. In terms of costs, roughly speaking, if you take, Dominic mentioned the 2.5 time factor for a standard segment. If you take on top the connections in between, plus the grouting activity, you look at factor 3 of one of the special segments to a normal standard segment. That was the end of the presentation. Thank you very much for listening. I hope it was interesting.
Great. Thank you very much, Michael, Dominic, and Xavier. I thought it was very informative, comprehensive presentation, open and honest, and I really like the way you talked us through the journey that you took on these cross passages. So, take some questions, please. Yeah. Questions? We've got one here.
Richard Dexter, Aaron Connect.
Right.
Michael, did you put any strain gauges or measure any of the stresses you were getting in the openings when you were opening them?
We did so twice, but if you're asking me now about the results, I don't have them in my head. But yes, we had 2 or 3 opening sets which were done with strain gauges, and the results are somewhere, but I can't tell you how they were. I can only tell you that the deformations were low and that the cracks, they almost did not crack. Once or twice we had on the back side of the segments some tiny cracks, approximately 0.1 millimeter. So you saw there must have happened some bending. The loads were there, but nothing that was, let's say, critical from a design perspective. It was all within the boundaries that we've been designing for.
Yeah, question.
Hayden Davis, I'm retired now. One aspect you didn't catch on is the durability of the segments, because there's a lot of steel in there. I noticed you had double coatings against that, but if you have cracks you mentioned which are 1 millimeter wide, certainly for the horizontal connections, how do you guard against corrosion of the rebar for a 120-year design life?
Yes. About the durability, the overall strategy was first to limit the crack width around 0.2, 0.3 millimeters conventionally as for the concrete. And for all the steel elements that are inside, First of all, the concrete by itself is limited in terms of cracking. That's the first point, no? Basically to limit the access of aggressive agents to the structure. And then the steel elements, or we have commented, truly we haven't going with all the particular details, no? But this is dowels has been protected, was coated, and later was injected. No, was some of the topics where we have some issues, no, to inject some of them. No, and precisely we make a protection because it's still inside the sleeve. There are some gaps, and all these special segments have different tubes and pipes, no, precisely to reinject that. Basically, for weighing assimilatory is how it's made in pre-stressed bridges, no, for how to deal for that, no, and basically what's the concept, no, that the no steel is in direct contact with air, crack white is limited, and also this additional coating precisely produce additional protection for ensuring the 120 years.
And for the scouting activities, we did also full mock-up and tested that one, that we really get a fully filled cross section.
Yeah. We tested the flowability of the grout with transparent sections. So you had one inlet and an outlet pipe. The guys were testing with a pistol, and you saw that it's flowing neatly and without any air voids. And we had in the ring joints, we had ceilings. So it was all filled later with durable grout. And only in the pockets where we had the pre-stressing rods, there were two alternatives. One is make the pre-stressing rods with stainless steel, then they are exposed, or fill the pockets later with something. But HS2 were unhappy about the reliability of anything that is, let's say, in the upper part of the tunnel, if it could come down in 20, 30 years, whatever. So we decided for stainless steel, and this is the only steel that is exposed. All the other steel has at minimum the concrete cover required for any rebar steel.
Yep, Steve.
Steve Parker, Keystone Tunneling. Excellent presentation. It's good to see the pros and cons of the approach. That was good. The dowels, because they're very stiff and large, and I don't know how many were per segment, 2 or 3. Did you have any issues when building the ring by the TBM? On Crossrail with the dowels, we had some issues where when you were shoving the ring home, the dowels actually caused some spalling and cracking if you had an ovality problem between the rings. So did the fact that the dowels were so strong cause you cracking when you were building the ring?
Steve, you mean the big steel dowels, not a standard one?
Yes.
No, that was the element that I mentioned before, that we pitched it quite well with the tolerances. I don't know, Dominic, do you remember how much tolerance we had?
No. Apart of the topic of the tolerance, the main business for ensuring that this is ensuring the transmission, basically these segments are composite structures. And then for ensuring the transmission, because always the topic is how to transmit these large loads in a reduced thing of the segment, is precisely all this is thing forward. For me, the main business is not to use a larger dowel. No, basically this is easy to check. The main business is how to deal with the transmission, and the transmission is achieved by that all the internal steel structure that really is working as a composite structure.
Yeah.
So there was sufficient tolerance between the dowel and the sleeve.
Yeah. I agree. The tolerance is the key, isn't it?
Yes, the dowels were loosely fitting. So we had the diameter of the dowel was approximately 8-10 millimeters smaller than the hole. And so they could easily insert the dowels without any constraints, and the grout did then the rest, that we filled the gap.
Good, that's the key. Thank you.
All right, got one online here from Richard Kaus. Wants to know what the steel ratio for the segments was in kilograms per meter cubed.
I can't tell you the kilograms per cubic meter, but I can tell you the segment thickness was 350 millimeter, and a cage weighed approximately 1.3 tons, including the steel elements.
Okay, thanks.
So full metal jacket.
Yeah. But we've been saving any rebar works in the cross passages, so you have to weigh this against another solution, where you usually try to create a collar which takes on the hoop forces of the segments, and we didn't have this. So our cross passages were just fiber reinforced. We didn't do any rebar works there. The rebar works were only with these large top connections, but not with the standard crossbar boxes.
Okay, another question?
Hi there, Emily Phillips from Mott MacDonald. I'm in the corner. I'm curious about the carbon impact of your super reinforced segments versus a typical typical special segment with a temporary frame which can be reused for multiple openings. Is there a significant difference in terms of steel usage?
I think this depends a little bit on the construction methodology, how much time you have, how much time you can reuse such a structure. Difficult to give you a number, but in the amount of openings that we created, eventually, yeah, difficult for me to answer because it would really depend on how big the frame is, how many times you can reuse it versus the steel grade. So I struggle a little bit to do the calculation, but I assume we would have several sets needed, definitely. And such a bracing has got a little bit more steel than one of the openings. So they look massive, but on the other, it's a limited amount of segments. And I'm pretty sure, seeing all our other temporary works, it would have been more.
Thank you.
Any more questions? Yeah.
Paul Perry from ACOM. You showed at the beginning sliding doors at the cross adits. Did you have to make any provision for fixing or casting elements in your in what you were building, or noting that President Trump there was a bit smaller than the opening? Maybe there was some form of second stage in situ connection, and you didn't need to make any coordination or provision for those sliding doors.
So we have got some inserts in the segments, but the remaining surfing afterwards also we use them in temporary stages for hanging off ventilation duct and so on. They serve afterwards for rail systems of fixing their installations. I think we also partially use them for the doors or not but mainly is it as a connection then, or to get just a mold against it? Not 100% sure.
Yes, in the design for the connection, also this frame casting, no, we take advantage, no, all these plugs that are vivid, basically for temporary work, for fixing all the elements and avoid drillings inside the tunnel, no, was also used for connection of these casting frames around the doors. Yes.
Okay, thank you.
Another one online then. This is from Ashish Thacker and wants to know, did you explore the use of steel fibers in the segments?
Yes, we did. At the very beginning, this was a long evaluation. So we have got steel fibers in the Atlas Road Tunnel. At the beginning, in the ECI phase, we did an evaluation what is more cost effective, in that case also more carbon friendly. Is it a slightly thicker segmental lining? We went for the thinner segmental lining with the rebar. Dominic, maybe you can say some sentences. You have received several challenges around that.
Yeah, it was a very long debate, and we put in some thoughts about this. In the end, it was the geology, mainly in North Road Tunnel West. It was quite challenging. We had all these sand layers at the very beginning. We have heavily over-consolidated soils. They are more over-consolidated than ones in the center of London. So we were uncertain about the stresses. We checked for steel fibers, certainly. The initial proposal was a 400 millimeter lining, and the other contractors went with a 400 millimeter lining for HS2. And we also checked for 350 millimeter rebar lining in North Road West. We have 340 in North Road East and 325 in the Houston Tunnel. And the outcome was that we can do a 350 lining with minor reinforcement, approximately 60 kg per cage. And that we still managed to work all the openings along the tunnel. And so in total, the benefit over a fiber lining, which would have been a bit thicker, and we couldn't have done 350 with fibers only, or we were quite confident that we would have at least a third of a third or so of the drive that we would have needed rebars anyways. We went for a production with rebars only.
So
And
thicker lining would have meant also more excavated material driven around. So like Dominic mentioned, we went for the thin solution, but adjusted the rebar depending on the load situation. So we've got normal cage, heavy cage.
All right, I should add that Ashish said thanks for an amazing presentation.
Thank you.
All right, any more questions? Okay, and one more's coming online. Alessia Menini. From a design for construction perspective, how did the propless opening set change the balance between structural redundancy, safety margins, and buildability compared to traditional propped openings?
I think from the safety point of view, we didn't have any temporary work, so it's just a normal ring building. The ring building we can control. We've got the installation over there. That would be, I think, the safety aspect.
And in terms of structural performance, no, always the question of redundancy, no. This system is not simply determined because basically always in the tunnels we have additional behaviors, no. Let me explain. Basically, we have explained and we don't have collars, no, to fit the whole forces, but transversally we take into account that the cross passes, the top ventilation is restraining to outside the tunnel segments. Also, we have an additional process, no? Always the tunnel segments, and Michael knows well, no, that to remove a segment is next to impossible. No? Why? Not by the rebar, it's basically because always we have some remaining residual proportion force between the segments. Then in terms of the design, no, one reservation of redundancy on the behavior is that basically always in the tunnels we have some residual proportion force that precisely helps to work in a pipe process. No, basically all this system, but really what looks for is to ensure, no, that this behavior, looking for a more pipe behavior, no, to pitch the loads around is working. No, and the other point important in terms of redundancy, as Dominic has shown, no, this connection has a really ductile behavior. That is really important for us, no? Because in terms of something is going wrong, the displacements could be really large until there is a really lack of capacity, no? And then basically the design, the main goal is not only to deal with large loads, also to deal in a ductile way.
Thank you. Maybe one more question? No? Okay, well, thank you very much. Just a few closing slides then. So the drinks and food tonight, sponsored by Skanska and Strabag and Costain. Thank you very much. You heard John Scully speak earlier. John, I think this was put out. John died just before Christmas after quite a long illness. And I went to hear wasn't his funeral, it was a celebration of his life on Monday, which reflected the character he was. John organized the very successful evening, our annual dinners for 27 years. And he was the man that his opening statement when he wanted to join the BTS committee was he would vouch, or he would set up sausage and chips after these evening presentations. So you can think of him when you're having your sausage and chips tonight. Meeting's coming up then, the 12th of February. What is quite appropriate, I spoke earlier about this collapsed segmental line tunnel. I believe that was to do with the cross passage construction, but we'll hear for sure in February. And Jung is going to speak on that from Arup. 12th of February, that's here. The 19th of February, the BTS young members, they'll be given a talk on hyperbaric works and hyperbaric interventions. So it's most likely, I think it's pretty likely that's going to happen. Still looking for, or the application's still open, entry for the Harding Prize competition. This is open to young tunnellers under the ages of 33. We have 3 entries so far. Closing date's the 31st of March. The best papers will be selected to give a presentation here in March. So I'd encourage you, if you've got any young members, get the paper in as quick as possible, and the more we get, the better. And bookings will be open in a couple of weeks' time for the very successful BTS Design and Construction course, which is at Warwick University between the 6th and 10th of July. So bookings will be open on the website. I mentioned about John Scoley and the annual dinner. Again, bookings for the very successful annual dinner will be open on the website from the 1st of February. Ticket price gone up just a little bit this year, but that's, so it's 190 per person, and that's Friday the 8th of May. So our usual date, as in first Friday after the first bank holiday in May. Reduced price for young members, student and retired members. This is a bursary for attending the World Tunnelling Congress in Antwerp. You can apply, young members can apply, and the closing date for this is in July 2026. So 2 young members or students are sponsored by the BTS to attend the World Tunnelling Conference, which will be in 2 years' time, 1 year time, sorry. And the biannual BTS conference is available now for booking. Pre-registration, I believe there's subsidized rates if you get in early. And that will be on the 6th and 7th of October, just around the corner at the QE2 Centre, same place as it was last year. The BTS at 50 book, there are still a few copies available. You can get them through the website. We're talking a lot to schools, universities, museums is the latest. We put 5 in the Brunel Museum that were sold. They're still proving very popular. So we still have a few copies available. And membership, encourage anyone who's not a member to join the BTS Society, take part. It's very good value and you get a lot of benefits, and also our young members as well. Right. Feedback, QR code if you want to give some feedback. That would be great. That's it. Thank you very much. See you in the bar.